Hello and welcome to lecture number 7 of photorealistic and non-photorealistic rendering. I'm your instructor as always, Leslie Eisted, and in today's lecture we are going to wrap up our discussion of photorealistic rendering with a smorgasbord of topics that we've kind of left, but hopefully it'll kind of fill in the remainder of our picture of how to create a photorealistic image. Just a few things before we dive into that. Of course, assignment 3 is posted if you haven't taken a look at that. The other thing is that we'll be posting tutorial slides almost every week now on Brightspace, so make sure you take a look at that. The other thing is that your midterm is tomorrow. If you haven't seen the test midterm, which was really just a few questions, sample questions, please make sure you check them out, as that will become unavailable later tonight. And then the midterm, of course, will be on Tuesday morning at 8:30 till 10:30 or something like that. Now, what's the format of the midterm? So it's an online quiz, just like the sample questions that were provided to you. There are true-false questions, there are multiple choice questions, there's fill in the blanks, there's ordering questions, things like that. There's also some small calculation questions as well. Really, the questions that were presented as the sample questions were a direct comparison to what you should expect to see on the midterm itself. The coverage of the midterm is lectures 1 through 6, so this lecture is not on the midterm, so no worries about scrambling to learn today's content for tomorrow. But other than that, I think it should be fairly straightforward. It's open book. You can use the slides, you can use the videos, whatever you like. And apologize for the scratchy voice. We'll try to get through this. All right. So let's look at our wrap-up. So I want to start by talking about a couple effects that are related to the camera, because that's something we haven't really talked a lot about. When we were looking at the perspective view transformation matrix, you notice that the field of view and the near and far clipping planes were taken into consideration, but we didn't really account for all the varying parts of the camera and the different effects that you can create. And if you open up anything like Houdini, let's just open Houdini up here, and you open up the camera, I'll move it so it's in view here. There we go. And on the camera, well, that's not what I want. I didn't want to double click on the camera. And you go to render and view, you can actually see here's a bunch of parameters for the camera itself. We can set the focal length and the aperture. And then if we hit sampling, we also have a focus distance and an f-stop and a kind of bokeh that you want. But we haven't really talked about how to get these effects. Now, I'm not going to talk about how to get things like bokeh and so on, but what I did want to talk about is how to create the depth of field effect. Because when you're actually creating a photorealistic scene, this is actually a really powerful tool. Because when we think about photography, it typically has depth of field in it. And what's really nice about depth of field when we are doing rendering is we can kind of use it to hide things that may not be so accurate. So you could use depth of field to hide things in the background and also hide things in the foreground, which is kind of nice. But how does that actually get implemented? So just for reference, for example, now this is a photo. This is not a rendered image. This is an actual photo. But if I were trying to create this particular image and turn it into a photorealistic rendering, I would note that organic materials are exceptionally difficult to create photorealistic versions of. And so by having just the rose itself in the main focus area, I can blur out the regions behind and I won't notice if it's just an image. So this is the kind of thing that why we want it, even though, yes, this is a photo. Well, in In order to create this, we have to make the observation that depth of field is actually a product of the camera lens itself, the actual mechanics. We have the aperture, which is how much is open to light. So in this first diagram here from Wikipedia, you can see that the aperture is all the way open. And then for the second one here, where we have a small aperture, you can see here that it's very small. So it's how much light are we actually letting into the camera. Then we have the idea of lens focal length. So where is the lens actually going to be focusing? And what is the length or the size of the region that it's capable of focusing on? And we also have this issue of the circle of confusion. Now, what we can see here when we take these things together is that when you have a large aperture, you've got three different objects, the red one, the blue one, and the green one. And yes, they are flipped upside down here, and that is because, of course, that's just how lens optics work. So the object number one, which is really far away, when it goes through the lens, we can see here that the focal point of where number one comes into focus is not on the image plane. It's before the image plane, which means that it's going to be out of focus. Likewise, the green lines are going to be focusing beyond the image plane, which means they're also going to be out of focus. And only the things that actually come into focus at the point of the image plane will be in focus in the image. So here we're getting some depth of field from objects that are in front and objects that are behind. Now, how aperture can play a role here is you can see here that even though object 1 and 3 are still out of focus, what's interesting is that the size of the objects is changed due to the size of the aperture. So you can see from these diagrams how aperture and focal length can really impact our implementation of depth of field. Now, this is just looking at the physics of it. When we actually implement it, though, we are going to recreate these diagrams just with rays now. Now, originally what we had, I can actually break out something to doodle on here. What we used to have was a camera. And then we had an image plane, and we would send a ray into the world through some point in the image plane. Well, we're not quite going to do this anymore. What we're actually going to do is we're going to effectively simulate the lens being in front of this. So what we're doing now is we're going to send a ray through the original image plane, and it's going to go through the camera lens, and these lines are a little bit out of whack. And it's going to go through this fake circular lens that we've placed in front of the pixel, and that is going to bend the light, and it's going to go through another pixel on our new image plane into the world. And how the light rays are bent according to this artificial lens is going to create a focal distance, and the focal distance will be from the center of this lens to the center of this point here. Now, we can't just send one ray in order to do this, because if we did that, then it wouldn't make a lot of sense. So what we actually do is instead of sending one ray per pixel, now we're going to send a whole bunch of rays per pixel. And effectively what we do, I'm going to open up my diagrams here, is we've got this fake lens, and we're going to subdivide it into a grid. Now, the truth is you don't have to use a circle to get this effect. You can actually just do a rectangular or square-based grid. But in each of the little grid elements, we are going to choose a random spot. And we're going to send a ray through each of these random spots in the lens. And then we are going to compute the average over all of these rays that we send through the lens. And that is going to give us the blurred effect. It's actually quite simple to do. Probably the hardest thing, though, is actually computing the aperture and the lens, but there's basic math available online for you to see that. And if we go into things like Houdini, this is very easy again to do. We can set the focal distance here. We can set the f-stop here, the bokeh, and then the aperture you can set, of course, over here. Now, when we do this and we send multiple rays per pixel, that is going, and then we average the results, that will give us the depth of field that we want. It's not the only way. So one of the problems with that particular method is that you have to send a lot of rays. If you only send like 4 rays or 16 rays, you are going to get a very grainy looking depth of field or a very blocky looking depth of field. What you really want to do is send 25 or more rays, so a 5x5 or higher grid size, because you want there to be as many samples as possible to give you the softest, most realistic results. So it's a little bit slower because now instead of having 1 ray per pixel, you could have 25 or 100 rays per pixels. Another approach that you can use to create depth of field, and there are a lot of different approaches, but this is one I've also used, and this is you apply a Gaussian blur or any other kind of blur to pixels at different depths. So for example, what you would do is you would find all the pixels at the furthest depth and you apply the largest Gaussian blur to them. And then you take all the pixels from the next layer in front and you apply a slightly smaller blur to them, stick them on, composite them on, with each one moving towards the focal region, having less and less blur applied. And then as you move away from the focal region again, you start applying more and more blur. And that is another way that you can simulate a depth of field effect. It's actually a little bit cheaper to do this, but the results are not as accurate. I've actually used this depth of field technique that's described here to add depth of field to stereo 3D images, which did not have depth of field to start with. So what this ends up looking like, so this is just 3 random metallic balls in Houdini, and this one has no depth of field applied to it. So you see, as you can see, each of these spheres is perfectly crisp and clear. We can see everything nicely in them. When we adjust the parameters for the depth of field, it now takes the other balls out of focus. So the front one is still perfectly in focus, the blue one is starting to get out of focus, and the red one is even more so out of focus. And maybe you can't see this that well on this particular image in the video feed, but this is actually kind of grainy, and the reason why it's grainy is because we didn't send enough rays per pixel. If we send more rays per pixel, you will get a much smoother result. Now that actually leads into a discussion of something that if you do any reading about depth of field for ray tracing online, you'll come up with this word, distributed ray tracing. And I want to say it's such a bad name for what this is. Because when I think of distributed, I am not thinking of what they're referring to. When I hear the word distributed, I'm thinking of taking the job of ray tracing and distributing the work over multiple computers. That is so not what they're referring to here. What distributed ray tracing actually means is that we are distributing the final results computation over a multitude of rays. So it means we're going to send more than 1 ray per pixel, and the final color is the average of all of the results of those rays. And there's 2 different I mean, you can do lots of different things with distributed ray tracing. Depth of field is one example of an algorithm that uses distributed ray tracing. Another is anti-aliasing. We have seen before that when you send only one ray per pixel, that the image is still kind of blocky. But if we send multiple rays per pixel, we get smoother, more accurate results. The best way to do this is, again, to form that grid in the pixel, and then for each grid point, or each grid square, you're going to choose a random position inside of it to send a new ray. So that slight perturbation is going to give some variation in the direction of the array. And then we average all the results up and we get a nice smooth result. Now, distributed ray tracing is also known by others as stochastic ray tracing, although I have not seen it referred to that very often. And obviously, if we're doing distributed ray tracing, it is going to be more expensive because now we are sending, once again, more rays into the scene. So another camera thing we should talk about is stereo 3D cameras. When we're filming a movie that does real stereo 3D of like a real shot, there's a few different ways that people do it. They can either film it in 3D using two cameras, or they can convert it to 3D later. One of the advantages, of course, of an animated movie in 3D is that you can just render it from day one in 3D because the camera isn't real either. And how we render or create that 3D effect is, well, we have two eyes, which means that our brain is processing two separate images. And so we're going to render the scene using two separate cameras. Now, how we get that illusion of depth is actually if you know that when you have two images that were taken with a small separation between them, objects are going to be at slightly different positions in the left and right. So here's an example here. This is actually a ray traced 3D image. This does not use Houdini. That's why there's no logo here. This is my own homebrewed ray tracer. But you can see that the objects in these scenes are actually in different positions. Not all of them, but some of them are. That small amount of horizontal separation, this is a slightly better way of looking at it, the small amount of horizontal separation, your brain actually interprets that as depth. So when we want to ray trace a 3D scene to give that illusion of depth, we need to actually have two cameras which are horizontally separated. And that's exactly what I've done in my own ray tracer, is I have a special stereo camera object, which is just two cameras that are having the same parameters, but their position is separated by just a small horizontal distance. And if you open up Houdini, they actually have a stereo camera built in. It's right here. We can drop it into the scene. And then you can go over to view, and we've got things like aperture again, and that's going to control the aperture for both lenses. Now there's a special stereo settings, and in stereo settings, we can actually set some of the stereo properties. For example, the interaxial distance, which is the separation between the two camera lenses. Now, when we're talking about the human visual system, we talk about interocular distance, which is the distance between your two eyes, the center of your eyes, pupils. But on a camera, we've referred to it as interaxial, or IA. So right now, this is set to 0.075. And I can increase it, and what you can see here is the two little reference cameras are actually being exposed. Now what's really cool is if we actually look through the stereo camera, we have nothing in the scene here. We should put an object in the scene. Let's put an object in the scene. It's in front of the camera, so that's not very useful. So let's push this behind the camera. There we go. And let's push this down. There we go. So now when I look through my stereo camera, I see the ball, and there's two copies because one of them is for the left eye and one of them is for the right eye. And if I click on that stereo camera rig again, and I go back to the inner axial distance, I can pull it together and push it apart. Now, what is the effects of changing the inner axial distance? The effect is going to be when you have a really small inner axial, the amount of separation between the images will be very, very small. And that is actually going to be interpreted as flatter or less depth. Whereas when you have a large inner axial, that is giving you more separation, which is generally interpreted as greater depth. All right. So that's fun. So you don't have to use a stereo camera. So some applications like Houdini do have specialty stereo cameras just for this. My own ray tracer, I did build a special stereo camera just for it. If you don't have access to one in whatever rendering tool you're using, don't fear, because all you need to do is create two cameras. That's it. So I could have created, instead of this stereo camera, I could just have created two regular cameras and then rendered once with cam 1 and then rendered once with cam 2. That's all you had to do. And really what the stereo camera is giving us is now if we want to render an animation, we don't have to render it all with the first camera and then render it all with the second camera. It automatically takes care of that for us. All right. So that's how you can actually create a stereo camera. There's nothing really to talk about in terms of its implementation because it's just two cameras. But what we never talk about is how do you view this? So in Houdini, one of the things that you will note is the fact that when you look through the stereo camera, one of the images is red and the other one has a cyan tint. And this is known as Anaglyph. And there's lots of different variations for Anaglyph. Red cyan is a really common one because it gives us some color in our view. And the idea is you would actually be looking at the, it's grabbing in here, the things I have around my desk. You would be looking at the scene with these lovely fashionable glasses, red cyan glasses. And the eye that has the red would see one of the scenes, and the eye that has the cyan would see the other one. So it's a way of filtering out such that one eye gets one image and the other eye gets the other image. This is imperfect technology. There's a lot of bleeding between the two that's going to cause some discomfort. The other thing is that certain colors don't show up very well with red cyan. So it's not perfect technology, but there are other Anaglyph options. For example, you could do red-blue, which only does grayscale images. And of course, another kind, which you're probably familiar with, is if you've ever gone to a movie theater to watch a movie in 3D and they give you those polar glasses. They're the weird sunglasses with the slightly gray lenses. That's actually a form of Anaglyph too, except instead of giving colored lenses, they're polarized lenses. But it's the same idea. Each lens has a slightly different filter, even though you may not be able to perceive it. And it's going to make it so that the left image is given to the left eye and the right image to the right eye. Now, other ways that you can view stereo 3D images include things like free viewing. And this is where you just have the two images side by side and you can just do it. Some people find it easier to do that cross-eyed. I can't do any of it, but I've heard some people can do it. Another technology is active shutter, which I will reach into my box of mystery objects because I just so happen to have active shutter glasses there. And active shutter glasses, if you have a stereo 3D TV at home, there are these cool things here. Yeah. They don't fit over glasses very well. These are actually powered glasses. And you have to charge their batteries up and all of that fun stuff. And they look very innocuous, but actually, these lenses are LCD panels. And when you sync them with the television or the screen, they actually alternate flashing black. Now, you can't perceive this, but what it's doing, because it happens at a rate that the human visual system won't notice. But the idea is that the TV is going to alternate showing you left, right, left, right, left, right, left, right, really, really fast. And then these are going to alternate blocking out the eye that's not supposed to be looking right now. Hence, they have to be synced to the TV to make sure that you're getting the right synchronization. Now, these have kind of fallen out of fashion because these lovely glasses are incredibly fragile and incredibly expensive. Which is why I keep them in their lovely cases, so that they don't get destroyed. Now, there's all kinds of other different things that you can use for viewing stereo 3D content. If you're just using an image, this is a lovely technology for doing just images. These are ViewMasters. It is just a stereoscopic 3D viewing device. You look like this. They have these cool wheels. And the idea is that the image here and the image on the opposite side, the camera, this is going to be for the left eye and this is for the right eye. And this stereo device just makes sure that the right image gets to the right eye. Yes, these are very old. And you might be like, but they don't make those anymore. And I want to tell you, you are right. They don't really make them anymore. It's not here. I have all kinds of fun things in my house. Ha! Found it. You can still get these. So there are companies out there where you can actually get your stereo 3D photos printed as ViewMaster reels. So that's one alternative you have for that. So we've got Anaglyph, we've got Freeview, you've got active shutter with a television, you've got lovely stereo devices like the ViewMaster, and then there are also glasses-free displays. I don't unfortunately have any of those in my arm's reach. But that's things like lenticulars. If you've got a Nintendo 3DS, that is a parallax barrier display where you don't need anything. It just lets you view 3D. The back of my 3D camera actually has one of those on it. But those are special lenses that make sure that they are projecting the right content to the right eye. Which is kind of cool. So that's how you would view it if you were to render a stereo 3D image. All right. Now, I want to talk a little bit about performance, and this seems like a good opportunity because we talked about distributed ray tracing. Throughout the last 6-7 lectures, we have repeated the line, ray tracing is expensive. Global illumination is expensive. Radiosity is expensive. Path tracing is expensive. Rendering is really expensive. And the more quality you want, the more time it's going to take. So we need to find ways to actually improve the cost. Reduce it. So here's an interesting observation. thinking back to the ray tracing and the ray casting algorithm, we note that the work that each ray does is completely independent of every other ray. Now, that's not 100% true when we're thinking about distributed ray tracing, but actually kind of is. Because even if we need 100 rays to be sent in order to get the color of one pixel, each of those individual rays technically is working completely independent of all of the others until the very end. So since the rays' operations are completely independent, it makes them a key candidate for parallelization. Now, what do I mean by that? So there's two different ways that you can operate. You can operate serially, which is like a lineup. So all of the little triangles get in a good line, and they each go one at a time. So this triangle goes, when this triangle is done, then the next triangle goes, and then the next, and the next, and the next. That's serial execution. And the ray tracer that you implemented or helped implement in assignment 1, that was a serial ray tracer, one ray at a time, really slow. But what if you did this instead? What if we let each ray go at the same time? Is that even possible? It is possible. Not all of them can go at the same time. We're not, unless you're Pixar, which I'm not. But the idea here is that behind parallel is that instead of each ray waiting its turn, we're now going to say each ray gets its own computation device and we can compute them all at the same time. And I think mentally you should be able to see the difference between how fast this would be compared to how fast this diagram would be. But in order to make that possible, we actually need to have hardware that supports doing multiple things at the same time. And good news is we do have that. So you have two options. You have your CPU. So for example, that's your central processing unit, your main computer chip. My laptop, which is over here, has an Intel i9 with 8 cores in it, and each of those cores can run 2 threads per core, which means it can do 16 threads or 16 sets of instructions in parallel at the same time. So 16 rays can be computed at the same time. Not bad. The computer that I am recording this video on is a Ryzen 9, and that's from AMD. And it has 16 cores, and it can do 32 rays at a time. But my GPU can do more. So my desktop here has a 2080 RTX in it, and my laptop here has a 3080 RTX in it. NVIDIA cards. And the 3080 here has over 6,000 cores. And each of those cores can run a single thread, which means a single ray, which means I can do over 6,000 rays at the same time on my graphics card. It's really fast. Really, really fast. We can get hundreds of times faster implementation of these things using our graphics cards to do the job instead of our CPUs, which always leads people to ask the question, why don't we use our GPUs for everything? Well, there's a reason. A graphics processing unit is an incredibly specific device. It lacks a lot of general features that your CPU has. So it doesn't have things like branch prediction, which is something that helps predict whether you're going to take this, if this is going to be true or that's going to be true. And there's a number of other things that are causing the GPUs. They're just not meant for general execution, but they can do ray tracing, and they can do it really, really fast.